Hey everyone, welcome back to the channel. If you are a GCSE student in the UK and you have just started Forces and Elasticity, this video is going to be your ultimate revision guide. Whether you're doing AQA, edexcel or OCR, today's breakdown will help you smash those questions. So just grab your notes and let's make physics easy. So I'm starting with the very basic, the definition of the force, and here you can see it says it's pull or push. So obviously, like any kind of force, whether it's a contact force, non-contact force that we have studied earlier as when in forces and motion, we need to pull or push something, right? If it's a contact force, if it's a non-contact force, so that a touch is not required in that case. So we know that whatever be going to be the outcome, but to apply a contact force, you just have to touch a particular object. You have to push or pull. So let me see what a force can do to something. Starting, this is a stretch. So extension is when you apply a force. In this case, you are actually pulling from both the sides. You can see the direction of the force here. You're actually pulling, and this results in extending that particular object, increasing the length of that particular object, and this process is called extension or stretching. So this is an outcome. When you are pulling something, it will result in increasing its length. Now the next one is compression or squeezing. Now the force direction has changed. You start to apply, basically you're pushing kind of thing that you are doing and pushing it in towards inside towards the center. And when you do this, you are actually decreasing the size of an object, and that's called compression. So this is the original object where you are like squeezing it, you are compressing it, and this results in decreasing its size. The next is bending. So if you are again pushing, pulling at the same time, basically here and here you are pushing the different direction, you'll be able to bend something. Suppose if you are applying at the two ends, you are applying this force, what will happen that you are able to bend something. So still the application is the same, you are pulling or pushing, but the way you are doing so, that changes the outcome of it. And in this case, neither it's compressed or like tensed, or you haven't extended, but you have actually bent it. The next is move, that we have already studied in forces and motion, which results in moving something, a kind of motion you exhibit, the object exhibit. So when you push or pull, basically you are moving an object. Then it's rotating or turning. If your object is fixed at one point and you apply the force at other point, then you'll be able to turn it, which is also known as moments, and that we will be studying after this topic. So you are actually rotating it. And crushing, so when you are pressing, squeezing with a very high force in a random direction, you'll be able to crush something. So, and mostly the brittle materials are easy to crush in this case. So in that case, without a further deformation, you will be able to bring it to the breaking point. That's your crushing. In case of I was giving an example of a brittle material. That brittle materials are those materials when you apply force, they will not show you any extended elongation or deformation. They just got break very easily, got crushed very easily. So this is known as crushing, but that application of force results in crushing something. So these all are basically the outcomes of the forces. Because I was talking about the deformation, so deformation is basically a change in the shape. So if you are changing the shape of an object, doesn't matter, it has to be a very regular shape, extending, compressing, bending, it can be any. But if you are changing the shape, if you're distorting the shape of an object, that's called deformation. Now deformations are also two types that you can see clearly here on the screen. The first one is elastic deformation and second one is inelastic deformation. So let me see what is elastic deformation. So in elastic deformation, there is a temporary change. That means when you say, for example, if you are stretching something, when you are stretching and when you release the force, Because suppose this is an object and you have started pulling it, so it starts to extend like this. As long as you are applying the force, it keeps on extending itself. But when you release it, if it comes back to its original position, you were extending this. This is the first step. That means when the object was resting, then you start extending it. And then when you release the force, it comes back to its initial shape. And if it will happen, that kind of deformation is called elastic deformation, because you are applying the force, but upon releasing the force, it comes back to its initial position. So there is no visible change after the release of force, and that's called elastic deformation. Whereas the inelastic deformation is like the opposite of elastic deformation. In inelastic deformation, upon releasing the force, the material does not come back to its original position, and you will be able to see some permanent deformation. This is same, take an example, this is an object resting, and then you start basically extending it. That's the second step of it, and now you have released the force, so this happened. Upon releasing the force, it doesn't come back to its original position. It has to be like this, but unfortunately it's like this. There is a visible deformation of this length. You have extended it permanently, now you're not able to bring it to its original shape. So that deformation is called inelastic deformation. Now moving on to our next, Hooke's law. Well, as I told you, extension and compression, we have already discussed that. When you do so, it is definitely directly proportional to the force. That means if you apply more force, obviously you will be able to extend it more. If you apply a less force, you're able to extend not as compared to the larger force. So obviously I can say that they are proportional, and they are directly proportional. That means they share a direct proportion. So every time if you are increasing something, the deformation also increased by the same factor, but this is only up to the elastic limit. So I'll explain elastic limit as well, but when we will be doing graph. As of now, just understand Hooke's law, and just after it I'll be explaining the force extension diagram, and there I'll be explaining each and every term. Here understand that force is directly proportional to the, or extension is directly proportional to the force. When you keep on increasing the force, the extension also increases by the same proportion. That means when I apply the 1 Newton of force, and extension was 1 centimeters, and now I'm applying 4 Newton of force, extension would be 4 centimeters. Now it's 12 newtons, so extension is 12 centimeters, kind of this. That means every time you are increasing something, it is increasing by the same proportion. The extension is increasing by the same proportion. Or take an example, suppose you are applying 1 Newton of force, extension is 2 centimeters. Now you have applied 3 Newton of force, extension is 6 centimeters. If you are applying 9 Newton of force, extension is 18 centimeters. So you can clearly see they are bearing a proportion of 2, twice of it. So every time it's going to be like this, and definitely when you draw this on a graph, it will be a straight line. So I can say force is directly proportional to the extension, which is written here, and when we solve it, we need to remove this proportionality and introduce equals to sign. And when we introduce equals to sign, we have to introduce a constant, and in this case K is your constant, which is called spring constant. So what is a spring constant? If you have a difficulty in explaining something, the formulas are very helpful in describing the definition. We have F is equals to Kx. That means K would be F over X. Spring constant is force over extension. So from here I can say that the amount of force required to extend, to compress or stretch a spring or a material by 1 meter. So more specifically, I can say for the spring, that if the force required, it's the amount of force required to stretch or compress a spring by 1 meter, that's your spring constant. Because whatever be the force is required to stretch this spring by 1 meter, that will give you the spring constant, and that's the reason every material has a different value of a spring constant. So from here you can understand that every material is different. Some materials are very easy to stretch. That means when you apply a little bit amount of force, you'll be able to stretch it to the 1 meter. But there are certain materials, doesn't matter how much force you will apply, it's very hard. So that means if you want to stretch that particular object by 1 meter, you have to apply a very tremendous amount of force. So that describes the importance of the spring constant. That means the spring constant is actually a measure of how stiff a spring is, or how stiff a material is, and that tells the stiffness. It's simple. So it basically tells you stiffness. That means how stiff that is, not very much elastic, doesn't move or flow very easily. So that basically the stiffness. So if more is the spring constant, that means more the stiff that particular object is. I hope it's clear now, and we can move on to the force and extension diagram. First of all, you should know when you are describing or studying any graph, you should know that what should be there on x-axis and what's there on y-axis. Here, the force is drawn on y-axis and extension is drawn on x-axis. So we are basically looking into the behavior of a material on this graph, that when we start to apply the force, how the extension would work, what happens there basically. Now in this material, what happens is we have started applying the force. We are applying the force, and we can see that the extension is also increasing with the same proportion, just like I have explained previously in Hooke's law, that there it bears a particular ratio, a particular proportion. So if it's 2 times, so every time you increase the force, the extension would be twice of the force or thrice of the force. It all depends on material to material. So when you start applying the force, you started to increase the force, the extension is also increasing with the same amount. Now let's see the graph. When you're studying or describing any graph, the important thing is you should know which quantity is there on x-axis and which quantity is there on y-axis. Here clearly we can see the force is on y-axis and your extension is on x-axis. Now in this graph, as I explained you, the Hooke's law. So Hooke's law works within the elastic limit. Now let me explain you the elastic limit and limit of proportionality. And this is a very common, I can say, students really get mixed up very easily. They think that these two things are exactly the same, which is not in this case. Let me tell you, limit of proportionality. The Hooke's law, let me start with the Hooke's law. I think it would be much more easier. So Hooke's law says that force is directly proportional to the extension within the elastic limit. That means elastic limit is up to which your object will return to its original position. So if you are extending it and you, upon releasing the force, if it's coming back to its initial position, that's your elastic limit. But after a certain point of time, or point of you can say, if you exceed that and if you start applying the force beyond it, then there will be no more elastic deformation. It will enter in inelastic deformation zone. When you release the force, it will not come back to its original position, and that's your elastic limit. It can be here as well, it depends on the object to object. So it can be here as well, it can be here as well, but it has to be a point beyond it. Beyond that particular value, if you will apply the force, it will not come back to its original position. Now coming to this limit of proportionality. Limit of proportionality, that means the point up to which your object is obeying your Hooke's law, because Hooke's law says that force and extension are bearing the same ratio. If you increase the force, the extension will increase by the same proportion every time. But that will also work until a certain point, and that point is known as limit of proportionality. Beyond that, in this case, this is on graph, it's very easy to detect because that till that point it will be a straight line, and beyond that it will be a curve, which you can see here. Till here it's a straight line, and then it transit to a curve. So this is called limit of proportionality. Now let me tell you why these are different. Let's say this be your elastic limit, and let's see why these two are different. Because this is the point up to which it's a Hooke's law is being obeyed, up to which the force is directly proportional to the extension. They bear the same ratio. If extension is 2 times, then every time when you increase the force, extension will remain 2 times. But after that, even if you apply the force and upon releasing the force, the object will come back to its original position, but they no more are following the direct relationship. Now it's changing. That means if extension was following every time 2 times of the force, in this reason that's not happening. That means now if your, let's say, force is 3 Newton, so your extension is not bearing any particular scalar value or a constant proportion. It can increase variably, and that's the reason you will get a curve in this case. So that's why they both are not different. So I'm just again repeating, limit of proportionality is the point up to which Hooke's law is being obeyed. That means up to which the force is directly proportional to the extension. Extension is directly proportional to the force. But elastic limit is the point up to which the object behaves or shows an elastic deformation, and beyond it, it will show an inelastic deformation. Now, these are the terms that I have already explained to you. So that's the proportional limit or limit of proportionality. That means the point up to which the force is directly proportional to the extension. That means Hooke's law is being obeyed and is valid here. And in the graph we can see a straight line. So like till you have a straight line, it's actually obeying your Hooke's law. Elastic limit is the maximum force up to which the material will return to its original shape after removing the force. That means beyond it you will get an inelastic deformation. And graph is, that means there will be a straight line as well as some part of the curve you will be able to see till elastic limit. Ultimate or the maximum force. So on the graph, the point of the maximum force, that means this is the maximum amount of force that a particular object can bear before breaking, and that's your ultimate or the maximum force. In this graph, the point at which you can see the maximum force, let me delete this one, and I can clearly see this is that point, this one, let's say this one. So this is the point of the maximum force, and whatever be this value, that's called your maximum force, and this is the force that a particular object can withstand maximum, and beyond it, it will break. Next is the breaking point, the point at which your material breaks. That means it has failed, it will break. There will be a crack or something, but it will fail. So that's the point of breakage, and this is the point of breaking here in this case. That means after it has actually failed. So simple, it's a breaking point. So this was basically the graph of the force extension of a material. The next is the energy stored in a spring. Like how much energy, obviously if you are extending something on applying the force, the material is doing work. So, and we know work done is what? Energy transfer. Energy is actually being stored in a spring. While when you extend something, when you compress something, when you extend a spring or compress a spring, it stores energy, and that energy is known as elastic potential energy. It has its formula, which is this one. E is equals to half kx squared. Whereas, which I already explained, K is a spring constant. The unit is Newton per meter. It's easy. You can easily learn the unit of spring constant by its formula, which is F over X. force is Newton, extension is in meters, so K has a unit Newton per meter. And X is extension measured in meters. E is elastic potential energy, and any type of energy is always measured in joules. So this is the formula. Let me do 2 or 3 questions on it, but before that let me show you graphically. If suppose the question is on the graph you have to calculate the elastic potential energy, you should know that algebraically it's the formula which is half kx squared that we have to use in order to find elastic potential energy, but graphically it would be area under curve. If the question is you have to calculate the elastic potential energy till it obeys the Hooke's law, then this is the point where it's obeying the Hooke's law. Draw a straight line, you'll get a triangle, and the area of the triangle will give you the, so let's say this is the extension x and this is that f. So in that case you will get f half times f times x. And from here we actually find this equation which is half ke squared, because we know f is equals to kx. So when I replace this, it will give me half times k times x, which is half kx squared. That's what I explained, and that's why it's specifically mentioned for this one that this formula for the energy stored in a spring of elastic potential energy, this one is valid till your limit of proportionality or within the elastic limit, which is already mentioned here as well. This formula is valid only within the elastic limit, because we are actually calculating the area of this triangle. When I'm calculating the area of this triangle, that is giving me this formula. So if I increase that will be entirely different. So this formula is valid only till this point, half ke squared. As I told you that you want to calculate elastic potential energy, you have to find the area under curve. So then what you have to do is you can estimate the area. Still here you will get a very perfect answer. Beyond, if you want to calculate, you just have to estimate it. That means divide this into a trapezium and you can find the answer. So divide this into a known figure and estimate the answer for the area under curve, which will give you the elastic potential energy to that particular limit or to particular point. Well, in the next class we'll be studying about the experiment, and also we will be doing questions. So I have 2 different sheets. One sheet is very important for knowing the basics, how to solve, what is the basics of the theory, we'll summarize it, and also how to do the questions. And the next will be exactly the exam related sheet. You will find those questions that you can expect them in the exam. So these are very important, don't miss out those sessions. And also if you are looking for one-on-one online classes or group classes, they are highly affordable. I have tutors like university students as well as highly experienced tutors, and classes are pretty affordable. So all you need to do is just email us at exactacademy@gmail.com to book your free trial class for all subjects. We provide classes from year 1 till A levels for all subjects. So that's it for today. Bye everyone. Take care.